Hey everybody, I decided to go all in on this remote classroom thing just for one day because I was taking a look at our schedule of topics for the week. And we have two topics left, the divergence theorem and Stokes theorem. And the divergence theorem is actually really straightforward. So I figured instead of dragging everybody out of bed early on a Monday morning, I could just do this video in advance, show you a couple of examples, and we'll call it a day, and I will see you Tuesday morning instead, either live in person or remotely. Stokes' theorem will be a little more complicated than the divergence theorem, so enjoy this while you can. So the entire set of slides that's prepared for the divergence theorem, other than the title, there's two of them. So the divergence theorem is the second of these three conversion formulas or theorems that we're going to look at. We've seen Green's theorem, so you kind of get the idea by now, I hope, taking one of these more complicated integral types and turning it into another integral type, either A, just to make your life easier, or B, because there's actually a physical meaning underlying what's going on, and that's going to be true with the divergence theorem as well. So the divergence theorem requires that we have a simple solid region, meaning that we've got a three-dimensional solid region. It doesn't have breaks, so if you took an Oreo cookie and separated it to get it the creamy filling, you don't have a simple surface anymore, a simple region. But if you put it back together, then you have a nice little cylinder there, at least approximately. So you take this simple solid region and you recognize that, well, the boundary of it is a surface, right? And let's suppose we wanted to be going around this surface and doing a flux integral. We talked about those when we did surface integrals. We want to go all over this surface, like my coffee mug here, and here comes a force vector coming out of my coffee mug, right? F dot n right there. We want to integrate F dot n ds all over that surface to calculate the total flux that's going outwards or inwards around that surface. The divergence theorem says that we can either do that surface integral as a surface integral. We're always welcome to just do it in its given form. Or we can convert it to a triple integral of the divergence over this solid. Okay. So I'm going to show you here the two examples we're going to do. And then I'm going to pause for a second. I need to switch my camera to my document camera to show you some paper. But we're just going to calculate two flux integrals, one over a vector field zyx, using the unit sphere as A, our surface, but then also the whole solid. And then another flux integral for, x cubed, y cubed, z cubed is our vector field. And the surface that we're going to be talking about is going to be a cylindrical surface. Well, here, coffee mug again. Z equals 0, Z equals 2, unit circle and cross section. There we go. My coffee mug is the solid and the surface that we'll be talking about. So there might be a jump in the video here while I switch cameras. Okay, so I've switched to my little document camera here, which means I had to unplug my nice webcam, and you're looking at my mug. Take your pick which one, from the crappy laptop camera, but you don't need to see me. You need to be looking at what's on the bigger part of the screen. So what I've got here is just a diagram of the divergence theorem in action. So there's a big three-dimensional peanut, and this represents not only a surface around the perimeter, but also the solid that is inside that surface. And there's two things going on here. One is there's a vector field F that's in play, everywhere all over the diagram in three dimensions. And at points on the surface, we have normal vectors on the surface, and then that means we can also measure the component of flux perpendicular to the surface at all those points. And so this integral right here, we've talked about this. It's a flux integral, and it's calculating the total flux due to that vector field everywhere on and around that surface. And in our discussion of surface integrals, we only had one way to calculate that, and it was pretty gross. The divergence theorem gives us an escape clause, which under certain conditions, like the surface is nice and simple and smooth and closed so that it surrounds a solid region, we can trade the surface integral for a triple integral of the divergence of the vector field rather than the vector field itself. And physically, this means that the net flux around the surface is equal to the total amount of divergence in the vector field inside the region that the surface surrounds. Remember that divergence is a measure of compressibility. So a vector field whose divergence is 0 is incompressible. And in that case, the flow field would have to satisfy continuity of flow. Whatever flow goes in has to equal whatever flow goes out, because there's no more room in the flow field to allow for the generation of extra flow or the removal of flow. And so whatever, say, comes in through the left side has to be equal to what's going out on the right side. And so the net flux on the surface has to be 0. Whatever went in was also equal to whatever went out. But if the vector field is compressible, the divergence is non-zero, then you can have an imbalance between inflow and outflow, and the divergence theorem tells you that the total amount of flux around the surface, or in other words, the imbalance between inflow and outflow around the surface, is measured by the total amount of divergence of the vector field inside the region that's surrounded by the surface. So it kind of makes sense, I hope. So I'm going to flip to the next page. Okay, here we go. We're going to do the first example. We're going to calculate the total flux of the vector field ZYX over the unit sphere. Now what that means is we're doing a flux integral, which means we want to do the surface integral of f dot n everywhere on that surface. And in the surface integral section that we did, we would have to set up an equation that describes the surface. Now in this case, the unit sphere, we'd have to solve it for z. So we have z equals the equation of the surface. And so we could write the equation of the surface as square root of 1 minus x squared minus y squared. But recognize now that we're only working on the top half of the surface. So this means two things. If we're going to do this the normal surface integral way, not only would the integral that we have to do be gross, because we would have to set this thing up, remember that? So p, q, and r are the components of the vector field. Yeah, that's not too bad. But then gx and gy are the derivatives of the surface function, and those are going to be pretty nasty. Not only that, but once we've solved the equation of the sphere for z, so that we have that function, square root of 1 minus x squared minus y squared, now we're only working on the upper half of the sphere, meaning to get the total answer, we'd also have to do it over the lower half of the sphere, and that means we'd have to do one of these suckers twice. Okay? You're welcome to do that. If you like surface integrals, go nuts. Okay? But with the divergence theorem, we have an easy escape. And so we need to calculate the divergence of this field, which is just the derivative with respect to x of the first component plus the derivative with respect to y of the second component, etc. It's just 1. And so the divergence theorem says, well, hey, let's swap that surface integral that we don't want to do. Let's do instead a triple integral of the divergence of our vector field over this volume, the unit sphere. And the divergence is 1. So we're looking at the triple integral of 1 over this volume. And I can just tell you, and you should also know at this point, 4/3 pi. Because the triple integral of the function 1 over a volume gives you the volume of the volume. And this is the unit sphere. Its volume is 4/3 pi r cubed, where r equals 1. Now, if you don't believe that, you can go rig up that triple integral. I would recommend spherical coordinates, but yeah, it's going to be 4/3 pi when it's all said and done. Okay, here's example number 2, where we wanted to do a flux integral. The problem that I showed you on the slide presented it as the surface integral of f dot ds. Well, that's also just f dot n ds. Same thing. The geometry was a cylinder of radius 1 going from z equals 0 to z equals 2, and the vector field that we were integrating the flux on for this surface is x cubed, y cubed, z cubed. Now in this picture, recognize that this surface, if we just say it's the cylinder from z equals 0 to z equals 2, we might just imagine the lateral walls of the cylinder as our surface, but this thing has a cap and it's got a floor. And so if we include the top and the bottom of the cylinder at z equals 0 and z equals 2, now we have a closed cylindrical surface. Which means we can kick in the divergence theorem. The divergence theorem says rather than the surface integral of flux, we will do a triple integral of the divergence. For this particular vector field, the divergence is again pretty simple. It's 3 times x squared plus y squared plus z squared. That shouldn't be a surprise. And so we can take our surface integral that we don't want to do and trade it out for the triple integral of divergence. This is not as simple as the one before because this isn't just a volume calculation, but it's still going to be pretty easy because we're dealing with a cylinder, so we might as well use cylindrical coordinates, which means we can set up this integral with the appropriate limits. So we have the unit circle in cross-section. So the endpoints for r and theta are 0 to 1 and 0 to 2 pi. Sorry about the sloppy dr d theta there at the end. The function just becomes r squared plus z squared. Our dv turns into r times dz dr d theta, and I factored that 3 out front. And I went to Maple and said, hey, what is this? And Maple tells me that it's 11 pi. That's certainly easier than doing the surface integral. Okay, that's the divergence theorem. Certainly there are many more examples. The complexity of the example of any problem you do is going to be a mix of what does the divergence look like, as well as how nasty is the triple integral going to be. But those aren't problems coming from the divergence theorem. Those are problems coming from just doing triple integrals in general, right? So as far as the divergence theorem goes, that's it. We trade a surface integral for a triple integral of divergence. All the hard work kicks back to our work from weeks ago on triple integrals in different coordinate systems. And so if you encounter difficulties, it's going to come from that aspect of the problem. So go forth, try problems, let me know if you have any difficulties, and we can certainly talk about this more. But otherwise, that's our class for Monday. See you Tuesday.